Hello and welcome to this revision session for AQA A-Level Physics Paper 1 on the topic of electricity. So in today's lesson we're going to look at how to answer examination questions for A-Level Physics Paper 1 on AQA on the electricity module. So if we've been successful and we've learned in today's lesson, we can answer A-Level Physics examination style questions on electricity, assess our understanding on A-Level electricity, and then understand what topics of the A-Level Physics module of electricity that we need to improve upon. So how should we prepare for this revision session? When you complete your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side. In this section, write down your work and out or your answers to the questions in the revision session. When you're doing this, make sure to write your answers in full sentences and show your full working out. Whilst on the right hand side, write down any bits of information which you find useful or any hints and tips on answering questions from this revision session. After the end of the revision session, write up these notes into a revision sheet for you to use independently. So how should you be revising for your A-Level Physics? So the first thing you should be doing is learning the key facts. So using revision guides, class workbooks, student prep notes and the textbook to learn the key ideas of the course. You may wish to make a mind map or write out notes yourself. The second step is to test yourself. So use things like Caboodle, Seneca, a student knowledge checker to quickly test your own knowledge, and you may wish to do this from your own cue cards. And then finally, you would practice examination questions. So use exam prep books, homework books, supervised study books and additional workbooks to answer exam questions and mark your own work. And you may wish to download your own examination past papers to do this. So the three steps are to learn the key facts, then to test yourself, and then to practice examination style questions. So what questions will we cover in this revision session? Well, we'll have three types of questions. The first one are your general check questions. The basic questions designed to probe your understanding of the key concepts of the topic. The second one are the checkpoint questions, the more challenging questions designed to place your knowledge and understanding of the topics into different contexts and applications. And then finally, we've got the assessment point questions, which are past paper exam questions which will mimic the type of questions found in public examinations. So let's start with this topic of electricity. So the first question says, describe the difference between resistance and resistivity. Calculate the resistance of a copper wire of length 1 meter in cross-sectional area 3.32 times 10 to the minus 6 meters squared. The resistivity of copper is 1.7 times 10 to the minus 8 ohm meters. Then explain the effect of changing the temperature on the resistivity of a metal and calculate the resistivity of a piece of wire which has a resistance of 170 ohms when it has a length of 12 meters and a radius of 3 millimeters. So pause the video now, then unpause the video when you want to go through your answer. Right, the main difference is that resistance will apply to a particular component. It depends on the component's dimensions, whilst resistivity is a property of the material itself. The material will have a constant resistivity at the same temperature. Now, to work out the second question, you say resistance is resistivity times by length over area. The equation is given to you on the equation sheet. Pop in all the numbers and you get 5.1 ohms. The next one, we know that temperature affects resistivity. So when the temperature of the metal increases, the positive ions of the metal have more energy. This makes the positive ions themselves vibrate with a greater amplitude, which will increase the number of collisions between the charge carriers and the ions every second, so therefore it increases the resistivity. Now in the last question, it's the same equation as before. We've rearranged it to make resistivity the subject, but this time we need to work out area. So you're given the radius, we assume that it's got a circular area, so it's pi r squared. We convert our millimeters into meters, and we pop in all the values and we get 4.0 times 10 to the minus 4 ohm meters. The next question says, what is the resistance of a sample of copper 2 meters long with a 0.50 millimeter squared cross-sectional area? The resistivity of copper is 1.7 times 10 to the minus 8 ohm meters. Calculate the resistivity of a metal wire with resistance 2.5 ohms, length 1.8 meters and diameter 0.40 millimeters. Calculate the resistance of a copper rod of length 80 centimeters and diameter 0.5 millimeters. Then determine the length of nichrome wire of cross-sectional area 2.0 times 10 to the minus 7 meters squared required to make a 10 ohm resistor. The resistivity of the nichrome is 1.1 times 10 to the minus 6 ohm meters. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we're using the resistivity equation. So resistance is rho L over A, but the trick is we're converting from millimeters squared into meters squared. So it's 10 to the minus 6 because there's two lots of 10 to the minus 3s going from millimeters squared to meters squared. So we get 0.068 ohms. The next question is we're working out the area again, but remember we're given the diameter, so we half that to find the radius, and we convert those millimeters into meters to work out our area. We pop it into the equation and we get 1.74 times 10 to the minus 7 ohm meters. In question 3, again, it's the same idea. Remember, we're given the resistivity of copper earlier, and the resistivity of a material is constant. So therefore, we can say area is pi r squared. We can then pop it into the equation r equals rho L over A, and we get 0.069 ohms. And in this last one, we're rearranging. So now we're making L the subject. So L equals RA over rho. Pop in all the values, and we get 1.81 meters. The next question says, sketch a graph of I against V for a metallic conductor at a constant temperature and use it to describe Ohm's law. The current in a resistor is 0.50 amps and as PD across it is 5.2 volts. Calculate its resistance. Then define the ohm and express it in base units. Then a length of wire is connected to a cell. The current in the wire is 80 milliamps and the PD across the wire is 2.4 volts. Calculate the resistance of the wire. Then a resistor has a resistance of 1.2 kilo ohms. In 3.0 minutes, a charge of 54 coulombs flows through the resistor. Calculate the PD across the resistor. Then the current in a filament lamp is 1.5 amps. It is operated for a time of 1 minute. The charges flowing through the lamp transfer 500 joules of energy to the lamp. Calculate the resistance of the lamp. So pause the video now, then unpause the video when you want to go through the answer. Right, so in this first one, the graph of I against V should be a straight line through the origin, because Ohm's law states that potential difference is directly proportional to current for a conductor at a constant temperature. Resistance is given to you as PD over current, so it's 5.2 over 0.50 is 10 ohms. Now we can use this to define the ohm. So the ohm is defined as the resistance that a component would have when a potential difference of 1 volt is produced per 1 amp of current. Now you can see that from the equation R equals V over I, 111 there. Again, to work out the value in base units, you've got to work that through, but 1 ohm is 1 kilogram meters squared seconds to the minus 3 amps to the minus 2. The next question will use that resistance equation again, but remember we turn milliamps into amps, so that's times by 10 to the minus 3. In the next question we can work out V by doing V equals IR, but we've got to firstly work out what I is. So I is Q over T. Again, all these equations are given to you on the equation sheet. So it's 54 over 180 because we don't work in minutes in physics, we work in seconds. So it's 0.30 amps. Pop it in there. Remember, kilo ohms turned into ohms by times it by 1,000. So it's 360 volts. And in this last one again, it's a multiple step calculation. We know that potential difference is work done over charge, which is current times by time. Pop in all the values. Again, we don't work in minutes, we work in seconds. So we get 5.55 volts. We say R equals V over I, so we get 3.7 ohms. The next question says, fill in the missing values for current in the electrical circuits. So pause the video now, then unpause the video when you want to go through your answer. Right, it's important to note that the current through a junction, what was going into the junction must come out of the junction. So the first one is 2 amps. The second one is 2 amps again because it's all in one series circuit. Now for C, you'll notice it goes 3.2 at the junction. One of them coming out is 2.6, so what goes in must come out. So on the other side it must be 0.6 amps. Then they join again at the other side on that junction, so it comes out to be 3.2 again. And in here we've got it coming into the junction of 1.8 amps. On one side of the junction 0.6 amps is going out, so on the other side 1.2 amps must be going out as well. They rejoin up again at the next junction to give you 1.8 amps. The next question says, fill in the missing values for the potential difference in the following electrical circuits. So pause the video now, then unpause the video when you want to go through your answer. Right, in this question you've got to remember that the EMF in equals the PD out for each branch, and each branch will have the same overall PD out. So we know in the first one 10 volts is going in, so 10 volts is going out, so the one must be 4 volts. In the second one we know 6 and 6 volts are going in, so that's 12 volts, so it must be for B 12 volts in total because that's the only thing on that branch. But in the other one C must be 9 because 9 plus 3 equals 12. Now in D we know that 12 is going in, but we know that in parallel branches have the same potential difference. So for E it's in parallel with 4 volts, so it will have 4 volts, so therefore D will have 8 volts like so. And in this one we've got to be very careful because even though it's on the same line, it's on the same level as the two EMF sources, there's actually a 3 volt resistor there, so it's not producing EMF, it is in fact using up a potential difference. So the total input is 3 plus 9 volts, which is 12, so therefore we know that F must be 4 volts because we know there's 6 volts below it, and on parallel branches you get the same EMF in total, so 2 plus 4 equals 6, so you got 6 from there, you got 3 from the other resistor, so therefore you must get 3 as well. The next question again says fill in the missing values for potential difference in these electrical circuits. So pause the video now, then unpause the video when you want to go through your answer. Right, so again, we know EMF in equals PD out. So in this first one, we know it's 2.2 volts in, so the total must be 2.2 volts out, so that one must be 0.8 volts. Again, in B, we know that in total, we are going to have 8.7 out, so therefore we must have 8.7 in, so it's 3.7 there. Now in this next one you've got to be very careful because when you look at the orientation of the two cells, they're in opposite directions to each other, so we will consider one, most likely be 2.4 in this instance, to be a negative because the EMF sources are acting in opposite directions. So therefore the total going in is not 8.4, rather it's actually going to be 3.6, so therefore the other one is 2.2 volts. And in this one we know the total PD on that middle branch there, so we know it will be 9 volts, so it's 9 volts on the top one and 9 volts on the bottom. The next question says a 270 ohm resistor and a 170 ohm resistor are connected as part of a potential divider circuit to a 36 volt supply. The output is connected across the 270 ohm resistor. Calculate the output voltage, then outline how a pair of identical resistors can be used in a potential divider to produce an output of 10 volts from a 20 volt supply. Include a diagram in your answer. And then calculate the output voltage from the two potential dividers below. So pause the video now, then unpause the video when you want to go through your answer. Right, so we need to use our potential divider equation, which is V out equals V in times by the resistor which is being looked at divided by the total resistance, or you could say V is directly proportional to R. So in this instance we say V out equals V in times by R2 over the total resistance. So the resistance which we're measuring across is the 270 ohm, so it's 270 over the combined total of the two of them times by the input, which is 36, so we get 22 volts. Now a potential divider is fundamentally two resistors in series. Now to note, both resistors are equal, so therefore it'll split the potential difference equally because V is directly proportional to R. So you've got 20 volts going in, you've got 0 volts going out, and therefore each resistor has 10 volts going across from it being dissipated through it. This next one, we again use the potential divider equation. Remember, it is the wanted component's resistance over the total resistance times by the input, so we get 3 volts there and we get 48 volts there. The next question says, with examples, outline why it's necessary for different power sources to have different internal resistances. Describe what happens to the terminal PD from a power source as the current through the source increases. Then a 9 volt battery with an internal resistance of 2 ohms is connected in series with the filament lamp. The lamp draws a current of 1.5 amps. Calculate firstly the lost volts, then the terminal PD, then the energy lost per second by the battery, and then the resistance of the lamp. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, you've got to understand that the internal resistance will limit the current in the circuit because it's a series circuit, so therefore the current in both the internal and the external circuit will be the same. So therefore, if you have a low internal resistance, you will therefore have a high current in the circuit, and a high internal resistance will give you a low current in the circuit. Now we know that terminal PD is equal to EMF minus lost volts. EMF stays fixed, but the lost volts can be calculated by the current times by the internal resistance. So as the internal resistance is a fixed value, when current increases, the lost volts will increase, so therefore the terminal PD will decrease because there's a greater proportion of the EMF being lost as those lost volts. Now you can work out lost volts, like we said, by doing internal resistance times by current. You've got each of those in that example, so the answer is 3 volts. Terminal PD is EMF minus lost volts, so it's 9 volts minus 3 volts, so it's 6 volts. Energy lost per second is another name for power dissipated. We know that power equals I squared R. That again is an equation given to us on the equation sheet. We know the current in the battery because it's constant throughout the circuit, 1.5 amps. We know the resistance of the battery because that is what internal resistance is, the resistance to the power source. So it's 1.5 squared times by 2 is 4.5 watts. Then we know what for the lamp, we know what the current is. It's in series, so it's always the same. It's 1.5 amps. We know its potential difference because that is the terminal PD, because it's the only output to the terminal PD. So we get our answer to be 4 ohms. The next question says, a piece of silicon has a length of 3 mm, a cross-sectional area of 6 mm squared, and a resistance of 200 ohms. Calculate the resistivity of silicon. Then a tungsten wire has a length of 14.1 cm and a radius of 2.34 mm. Tungsten has a resistivity of 5.6 times 10 to the minus 8 ohm meters. Calculate the resistance of this tungsten wire. Then, a scientist is designing a circuit and needs a copper wire 1 cm long with a resistance of 0.000557 ohms. The resistivity of copper is 1.68 times 10 to the minus 8 ohm meters. Calculate the radius the copper wire needs to be. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we're using the resistivity equation. Remember, length goes from millimeters into meters. We know that millimeters squared goes into meters squared by doing times 10 to the minus 6. We work it through and we get 0.4 ohm meters. The next one again, we work out our area. We've got the radius, we convert that into meters. We then do pi r squared to then work out the area. We then say resistance is rho L over A. Pop in all the values. Remember, 14 centimeters turns into meters, so we get 4.6 times 10 to the minus 4 ohms. Then in this final one, we make area the subject in the resistivity equation. So we will convert centimeters into meters, and we pop in the values for the area to get 3.7 times 10 to the minus 7 meters squared. We then say the radius is the square root of the area over pi, rearranging the equation for a circle's area, and therefore we get 3.42 times 10 to the minus 4 meters. The next question says, there is a current of 10 amps through a lamp for 1 hour. Calculate how much charge flows through the lamp in this time. Then calculate the current in a circuit when a charge of 180 coulombs passes a point in the circuit in 2 minutes. Calculate the number of protons which would have a charge of 1 coulomb. In which of the following quantities of electrical charge is possible, and explain how you know this. 6 times 10 to the minus 19 coulombs, 8 times 10 to the minus 19 coulombs, and 10 times 10 to the minus 19 coulombs. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we can work out what the time is going to be, but we convert the time from hours into seconds. So it's 3,600 seconds. Charge equals current times by time. We've got the current, we've got the time, so we get 3.6 times 10 to the 4 coulombs. This next one, we know that current is charge over time. Pop in all the values. We don't use minutes, we use seconds in physics. So we get 1.5 amps. Now, how many protons would have a charge of 1 coulomb? So you do the number of protons in 1 coulomb is the charge in coulombs divided by the charge of 1 proton, or electron in this instance. So it's 1.6 times 10 to the minus 19, so that's 6.2 times 10 to the 18 protons. Now the only one which is possible is 8 times 10 to the minus 19. That's because we know that the fundamental unit of charge comes in multiples of 1.6 times 10 to the minus 19 coulombs. That is a fact in physics. So you can only find one which is a multiple of 1.6 times 10 to the minus 19, which is 8 times 10 to the minus 19 coulombs. The next question says figure 11.14 shows a piece of silicon of width 32 millimeters and length 36 millimeters. The resistance of the silicon between points P and Q is 1.1 mega ohms. Silicon has a resistivity of 2.3 times 10 to the 3 ohm meters. Firstly, calculate the thickness of the piece of silicon. Calculate the current that will pass through the silicon if a potential difference of 12 volts were applied across P and Q, and then discuss how the current would change if it was large enough to cause the silicon to become significantly warmer. So pause the video now, then unpause the video when you want to go through your answers. Right, in this first one, you've got to use the resistivity equation. So you say R equals rho L over A, but also area is thickness times by width. So you can work out the thickness by doing the area by working that value out, and then saying that the thickness is going to be the area over the width. So you pop in all the values. Remember, those width and length values need to turn from millimeters into meters. Be careful on that. So we get 0.024 meters. The next one, in terms of the current, well, current equals potential difference over resistance. We're given the potential difference in the question, and we know what the current is when you're working it through the resistance, because you're given the previous question, so it's 1.1 times 10 to the 6. So the answer is therefore 1.1 times 10 to the minus 5 amps. This next one, we've got to think about what would happen in this instance. Well, in this instance, the resistance would decrease and the current would increase, because the silicon, you've got to be aware, is a semiconductor. So in a semiconductor, when you increase the temperature, it releases more charge carriers into the circuit. That decreases the resistance and increases the current. The next question says, explain why the resistance of a metal increases when its temperature increases. State two of the factors which determine the resistance of a stated length of wire. Then, when a potential difference of 1.5 volts is applied across a 5.0 meter length of insulated copper wire, a current of 0.24 amps is measured in it. Firstly, calculate the resistance of the length of wire. Then the resistivity of copper is 1.69 times 10 to the minus 8 ohm meters. Calculate the diameter of the wire. Then the wire is now made into a tight bundle. State and explain how you'd expect the current in it to change. So pause the video now, then unpause the video when you want to go through your answers. Right, you've got to understand how resistance and resistivity is affected by the temperature for a conductor. So as we said before, when the temperature increases, the atoms vibrate with a greater amplitude, so therefore there are more collisions per second. That increases the resistance. Now, the other factors that affect resistance include the cross-sectional area, the length and the material of the wire. In this next one, how do you work out resistance? Well, it's V over I. You've got V, you've got I, so it's 6.25 ohms. This next one, we use the resistivity equation and we work out the area. So you work out your area to be 1.35 times 10 to the minus 8 meters squared. You can then say diameter is the square root of 4 times the area over pi. Okay, and then you can work it through to be 1.3 times 10 to the minus 4 meters. And in this last one, we notice that what happened to the current in it? Well, if you've got it in a tighter bundle, there's less area to the open air, so they're less likely to dissipate energy out to the surroundings, so there's less cooling, the temperature rises, therefore the resistance will increase for the reasons stated previously, so the current will go down. The next question says a filament lamp and a 220 ohm resistor are connected in series to a battery of 6.0 volts EMF. The battery has a negligible internal resistance. A high resistance voltmeter is placed across the resistor and measures 1.8 volts. Calculate the current drawn from the battery, the PD across the lamp, the total resistance of the circuit, and the number of electrons passing through the battery in a time of 1 minute. So pause the video now, then unpause the video when you want to go through your answer. In this first one, we know that current is going to be equal to V over R. We've got V for the resistor, okay, and then you can work out what R is going to be. So it's going to be 220 ohms. So therefore, it's going to be 1.8 over 220, which is 8.2 milliamps. Now, whilst you might think, yes, that's the current in the resistor, but it's also the current in the battery because they're in a series circuit and the current is constant throughout. Always look to what you can work out for particular components. The potential difference across the lamp is going to be 4.2 volts because the total EMF from the battery is 6. The voltmeter takes 1.8, so the lamp must be taking 4.2. Now the total resistance in the circuit must therefore be the total EMF divided by the total current, so you can work it through to be 6 over 8.2 times 10 to the minus 3 milliamps into amps, so you get 730 ohms. Now, how can we work out the number of electrons passing through? So you work out the charge. You know from the equation sheet, charge equals current times by time. Now 1 minute we convert to 60 seconds, so we get 0.492 coulombs. So therefore, to work out the number of electrons, you work out the total charge divided by the charge on one electron, so you get 3.1 times 10 to the 18 electrons. The next question says, explain what is meant by the internal resistance of a cell. When a cell is connected in series with a resistor of 2.00 ohms, there is a current of 0.625 amps. If a second resistor of 2.00 ohms is put in series with the first, the current falls to 0.341 amps. Calculate firstly the internal resistance of the cell, then the EMF of the cell, and then a car battery needs to supply a current of 200 amps to turn over the starter motor. Explain why a battery made of a series of cells would not be suitable for a car battery. So pause the video now, then unpause the video when you want to go through your answers. Right, in this first one, what's the definition of internal resistance? It's the resistance done to the work in driving the current through the EMF source or through the cell. Okay, now in terms of the internal resistance, we know from our equation sheet EMF is equal to current times by the external resistance plus the internal resistance. We can see the external resistance is 2 ohms from the information given. That's the resistance of the circuit in general. We've got the current, okay, so we know it to be 0.625 amps. Okay, we can see that we can link the two together by talking about, if you put a second resistor in series, it's going to turn to 4 ohms, pop them through, work out R, it's 0.40 ohms. Therefore, we can use this equation to work out the EMF by saying EMF equals I big R plus small r. We know small r, we know big R, and we know current is a combination, so the EMF will equal 1.50 volts. Now, you'll notice that when you put cells in series, the resistance of each cell, the internal resistance, will add. So therefore, if you put them all in series, the internal resistance will get too high, so you wouldn't get a maximum current above 4 amps due to this internal resistance. The next question says, a circuit diagram shown below shows a 12 volt power supply connected to some resistors. The current in resistor X is 2.0 amps and the current in the 6 ohm resistor is 0.5 amps. Calculate firstly the current in resistor Y, then the resistance of resistor Y, then the resistance of resistor X. So pause the video now, then unpause the video when you want to go through your answer. Right, you'll notice by looking at the idea that if the current in X was 2.0 and the current in the resistor was 0.5 amps, well, the current going into a junction equals the current going out, so it's 1.5 amps. What's the resistance of Y? Well, we know the potential difference across Y is going to be the current times by the resistance. So we know the current is 0.5 amps, the resistance is 6, so the PD is 3 volts. So therefore the resistance across Y is going to be R equals V over I. We know V is 3, we know the current is 1.5 from the previous question, so therefore the resistance is 6 ohms. And then for X, we can say that the potential difference across X, because we know that the other one's taken 3, this must take 9, R equals V over I, it's 9 over 2, it's 4.5 ohms. The next question says, a student connects the circuit shown. The battery has a negligible internal resistance. The student increases the resistance of the variable resistor from 0 ohms to 40 ohms. Determine the range of readings on the voltmeter. So pause the video now, then unpause the video when you want to go through your answer. Right, so this one is using the potential divider equation like we talked about before. Now, when the variable resistor is at 0, that is going to take 0 volts because V is directly proportional to R. So therefore, all the volts are going to go through the resistor and therefore the voltmeter because they're in parallel with each other. So we'll take them all from the battery, which is 6 volts. Now, to work out how much it would take when there's the maximum value for the variable resistor, well, we know that the resistor itself will have 10. The total in the circuit will be 50. So it's 10 over 50 times by 6, which is 1.2 volts. So there's the range of values your variable resistor would be measuring in the circuit. The next one says a battery of electromotive force 9 volts and negligible internal resistance is connected in series with an LDR and a fixed resistor of resistance 1800 ohms. A voltmeter is connected across the fixed resistor. The reading on the voltmeter is 5.4 volts. Calculate the current in the circuit. Then calculate the resistance RL of the LDR, and then the intensity of the light illumining the LDR increases. By reference to the current in this circuit, state and explain the change, if any, to the voltmeter reading. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, you know the resistance of the resistor, you know the current going through, you know the potential difference going through the resistor, because you know the value from the voltmeter. So you can work out the current for that resistor, and it's going to be the same everywhere because it's a series circuit. Always look to see what combinations of values you have given in that circuit. So the current is going to be equal to V, 5.4, over the resistance 1800, so you get 3.0 times 10 to the minus 3 amps. What's the resistance RL of the LDR? Well, you ratio the two of them because V is directly proportional to R. So if 1800 ohms takes 5.4 volts, what will 3.6 volts get you? Remember, because we know that if there's 9 in total and the other one takes 5.4, that one must take 3.6. So therefore we get our answer to be 1200 ohms. Now in this next one, you've got to be aware that when the light intensity increases on an LDR, that will decrease the resistance of an LDR. That's a fact you've got to learn. So if the total resistance of the circuit goes down because the LDR's resistance goes down and the other resistor is fixed, well, therefore the current will increase. So because there's a greater current going through the actual component, the potential difference will also increase, so therefore the voltmeter reading increases. The next question says a single cell of EMF 15 volts is connected across a 0.30 ohm resistor. The current in the circuit is 2.5 amps. Calculate the terminal PD and explain why it's not equal to the EMF of the cell. Then show that the internal resistance of the cell is 0.30 ohms. It suggested that the power dissipated in the external resistor is a maximum when the resistance R is equal to the internal resistance of the cell. Calculate the power dissipated when R equals R. Then show that the power dissipated when big R is 0.50 ohms and small r is 0.20 ohms is less than that dissipated when R equals R, as the above statement suggests. So pause the video now, then unpause the video when you want to go through your answer. Right, so be aware that terminal PD is going to be equal to I times by the external resistance of the circuit. So in this case, it's 2.5 times by 0.30, 0.75, and therefore that's the work, and the terminal PD is not equal to the EMF because the terminal PD you got to subtract the lost volts due to the internal resistance from the EMF. Now in this next one, we know E equals the terminal PD, I times by big R, plus the internal resistance times by small r, the lost volts. Pop in all the values, work it through, and we get small r equals 0.30 ohms. Now in this next one, okay, work out what the power dissipated will be. Well, P equals I squared R in this case, so it's 2.5 squared the current times by R, which is going to be the internal resistance because we're looking at the power dissipated in the cell. So therefore you work it through to be 1.88 watts. Now therefore you can work out the total power by working through again by I squared R, working the current when you got the total resistance in there to be 0.80 because we're adding the two because they equal each other. So therefore we get 1.76 watts. So why is it not the same? Well, you can work out by the values there, work them out together, work it through, and you'll see that both is less than 1.88 watts, so therefore it can't be the case. The next question says, explain the difference between the terms EMF and potential difference. Then figure 10.28 shows a circuit containing batteries and resistors. You may assume that batteries have a negligible internal resistance. Firstly, use Kirchhoff's first law to find the current in the 4 ohm and the 8 ohm resistors. Then calculate the EMF of E1, then the value of E2, and then calculate the current in the 12 ohm resistor. So pause the video now, then unpause the video when you want to go through your answer. Right, as we said before, the potential difference across the terminals of a battery, the terminal PD, is the work done per coulomb of charge in the external circuit, whilst the EMF is the theoretical work done per coulomb charge, okay, that goes into the circuit. Now in this next one, if we look it through using Kirchhoff's law, it's 0.75 amps, and then the EMF of this circuit, V equals IR. So we've got I, 0.75 amps, we've got the external circuit resistance, 12 ohms, so you can work it through to be 9 volts. Here again, use the circuit loop ideas with the batteries in both of them and the 3 ohm resistor. Again, total EMF in equals PD out. So the EMF of that particular component is 6 volts. So therefore the current is therefore I equals V over R. It's 6 over 12. It's 0.5 amps. The next question says, a nichrome wire has a length of 1.5 meters and a cross-sectional area of 0.080 millimeters squared. The resistivity of nichrome is 1.3 times 10 to the minus 8 ohm meters. Calculate the resistance of the wire, and then calculate the length of this wire which we needed to make an element of an electrical heater of resistance 30 ohms. So pause the video now, then unpause the video when you want to go through your answer. Right, how to work out resistance? Well, we've got to use the equation, the resistivity equation. R equals rho L over A. Pop in all the numbers. Remember, we convert the millimeter squared into meter squared, 10 to the minus 6. We'll get the values through, and it's 0.24 ohms. Now, this next one, we need to change it and make L the subject. So L equals RA over rho. Again, resistivity will stay constant because it's the same material. Pop in all the values, and we get 184 meters. The next question says, Figure 4 shows the IV characteristics of a slice of semiconductor material. Firstly, define resistance. Then show that the resistance of the slice is about 250 ohms when there's a current of 40 milliamps in it. Then the dimensions of the slice are shown below. Calculate the resistivity of the semiconductor material when there's a current of 40 milliamps in this slice. Then explain how the IV characteristic shows that the resistivity of the semiconductor material decreases with increasing temperature. So pause the video now, then unpause the video when you want to go through your answer. Right, so defining resistance. So look at the equation to help define it. So we can say that resistance is equal to the potential difference divided by the current. Now this next one, how do we show that the resistance is the case? Well, R equals V over I. Pop in all the values. Remember, 40 milliamps turns into amps, so therefore R equals 250 ohms. In the next question, work out the resistivity. Well, we know resistance is equal to rho L over A, so rho is equal to RA over L. Pop in all the values, work it through, and you get 0.30 ohm meters. Now in this last one, we know in the IV characteristic graph, okay, that when you got a semiconductor material, the graph will curve. So that indicates to you that the resistance of the material is changing. Now as it's curving, this tells you that the current is increasing faster than the potential difference is increasing. Now what's happening is the increased temperature is caused by the current. Okay, so therefore what you can therefore say is that as R decreases, because it's linked intrinsically to the resistivity will also decrease as well. The next question says, Figure 12.13 shows a potential divider. The battery has a negligible internal resistance and the voltmeter has an infinite resistance. State and explain how the read on the voltmeter will change when the resistance of the variable resistor is increased. Then resistor R2 has a resistance of 470 ohms. Calculate the value of the variable resistor when the read on the voltmeter is 2.0 volts. The voltmeter is now replaced with one of resistance 2 kilo ohms. Calculate the resistance on this voltmeter. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, what will happen is that you'll notice that as the variable resistor is increased, well, therefore, you can see that the current through R2 will decrease because you know that the resistance has gone up, so the current of the circuit will go down. Or you could say, well, when the resistance of the variable resistor goes up, the variable resistor will take more potential difference because V is directly proportional to R, so therefore the voltmeter, which is measuring the other device, will have less potential difference going through it, so its reading will decrease. This next one, we use the potential divider equation, pop in all the values, and we get 1600 ohms. Now this next one, the voltmeter has now got a resistance. It's now 2000 ohms. Now it's in parallel with another component. So we're going to have to use the parallel resistor equation to work out the total resistance of the resistor and the voltmeter. So it's 1 over 470 plus 1 over 2000, then 1 over that value. So so you get 380 ohms. Now remember, when things go in parallel, the total resistance is always less than any of the individuals, so 380 ohms makes sense. We can then pop that into the potential divider equation. Remember, that's the wanted output, so it's 380 over the total times by the input, which is 9, which is 1.7 volts. The next question says, the photograph on the screen shows a statue of the Buddha in Sri Lanka, which is protected by a lightning conductor. During a storm, the potential difference of 2.7 megavolts was generated between a cloud and the top of the lightning conductor on the statue. A flash of lightning passed between the cloud and the lightning conductor, producing a current of 25 kiloamps for a time of 7.5 milliseconds. Calculate the energy transferred by the lightning strike. The lightning conductor is a length of copper wire with a diameter of 1.2 times 10 to the minus 2 meters and a resistance of 4.3 times 10 to the minus 3 ohms. It runs along the back of a statue from the base to a height of 1.5 meters above the top of the statue. A guidebook claims that the statue is over 30 meters high. Assess the validity of this claim. The resistivity of copper is 1.7 times 10 to the minus 8 ohm meters. Then give a reason why the lightning conductor should be taller than the statue. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we need to work out energy transferred. Now we know that energy transferred is the potential difference times by the charge. Now we can work out the charge by doing current times by time. Now we are given the time, okay, as 7.5 milliseconds. We convert that into seconds. We then convert our current of 25 kiloamps into amps by just times by 10 to the 3. So we get our charge out to be 188 coulombs. Then we can say work done is charge times by potential difference. Pop in all the values. Megavolts turns into volts by doing times 10 to the 6, so we get 5.08 times 10 to the 8 joules. In this next one, we need to work out the length of the wire, so therefore we use the equation R equals pi r squared, or pi d squared over 4. We work out the area of the wire. We then use the equation for length, so length is RA over rho. We get our answer out to be 28.6 meters. Now it's important to note it said in the question that the wire was 1.5 meters taller than the statue. So the statue's actual height is 1.5 meters minus that value, so it's 27.1 meters, so the claim is not correct. Now the lightning conductor should always be taller than the statue, so the lightning makes contact with the conductor rather than the statue. The next question says, resistivity paper is paper covered with a thin layer of carbon. The distance between the ends of a piece of resistivity paper is 12 centimeters, and the resistivity paper is 4.2 centimeters wide as shown. The resistance between the ends of the resistivity paper is 8.8 ohms. Calculate the thickness of the layer of carbon. The resistivity of carbon is 3.7 times 10 to the minus 5 ohm meters. A student connected the ends of the resistivity of the paper to a cell of EMF 1.5 volts and the voltmeter is shown. The reading on the voltmeter is 1.4 volts. Calculate the internal resistance of the cell. Then the connection to the right hand terminal of the voltmeter was moved to a distance of 3.0 centimeters from the left hand side of the resistivity paper. Determine the reading on the voltmeter. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we need to work out the resistance from this. So we use the resistance equation, R equals rho L over A. But the trick is now, area is going to be thickness times by width. So like we had before, we pop in all the values. We therefore say area is thickness times width. We convert all of our millimeters and centimeters into meters. So we then pop them through and we get the thickness to be 1.2 times 10 to the minus 5 meters. This next one, we can work out the current. Now remember, you can do it either with the external circuit or with the internal circuit. Now with the external circuit, we know that it's 1.4 volts because it's running the voltmeter. We know what the resistance is externally. It's 8.8 ohms. It tells you earlier. So the current is 0.16 amps. Now because it's a series circuit, the current in the external circuit is the same as the internal circuit. So therefore, internal resistance is going to be equal to the value in the lost volts, which we know to be 0.1 because it has 1.5 EMF and then 1.4 terminal PD. So therefore the lost volts is 0.1, 0.1 over 0.16, it's 0.63 ohms. Now for this next one, we know that V is directly proportional to R and R is directly proportional to length. So if you quarter the distance from 12 centimeters to 3 centimeters, you will quarter the length, you will quarter the resistance, you will quarter the potential difference. So the answer is 0.35 volts. The next question says, in the circuit shown, the battery has a negligible internal resistance. If the EMF is equal to 9 volts, R1 is 120 ohms and R2 is 60 ohms, calculate the current flowing in the circuit. Then calculate the voltage read on the voltmeter, and then the circuit shown in the diagram acts as a potential divider. The circuit is now modified by replacing R1 with a temperature sensor, whose resistance decreases as the temperature increases. Explain whether the read on the voltmeter will increase or decrease as the temperature increases from a low value. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know that the equation EMF is equal to I times by R plus R, so you can work it through like so. So V equals IR, so therefore you can pop in all the values, work it through, work out the values there, and I equals 50 milliamps. Now this next one, the read on the voltmeter, well, V equals IR. We know the current because it's the same through both of them because it's a series circuit. So we know it's 80 milliamps or 0.05 amps. We know that R for this particular case is 60. So therefore V equals IR. So therefore it's 3 volts. Then this last one, we've got to be aware about how the temperature sensor works as the temperature increases. You've got to remember that as the temperature increases, the resistance of a thermistor, a temperature sensor, will always decrease. So therefore the total resistance of the circuit will decrease. That means the current through the circuit will increase because the total circuit resistance has gone down. So that will increase the voltage through R2 because you've got a greater current going through it. Or you could also say the reason is because if we know that in the temperature sensor, if R goes down, V goes down because they're directly proportional, so therefore the other device must have a greater value of V to satisfy Kirchhoff's laws, so therefore have a larger share of the 9 volts. So thank you very much for listening to this revision session on electricity for AQA A-level physics. If we've been successful and learned in today's lesson, we should be able to answer A-level physics examination style questions on electricity, assess our understanding on A-level physics for electricity, and then finally understand what topics we need to improve upon for AQA A-level physics on the idea of electricity. So thank you so much for listening to this revision session on electricity for AQA A-level physics paper 1. Thank you so much and have a lovely day.